Hey folks, in this video we'll talk about a new type of integral, a line or a path integral. So here are some of the goals I have set out for you for this video, and let's check it out. So when we talk about a line integral through a vector field, well, we'll start with a vector field. That's the thing we can imagine we're integrating. And we integrate along a path or a curve or a line. We'll call that C. So a good way to think about what these integrals will be asking is these questions. For example, if f is showing us the velocity of a stream, we might ask, if we're paddling a canoe along the path C, is the stream helping or hindering us? Or in a more physical sense, if f is a force field, that is, each vector represents the direction and magnitude of the force at that point, then if the force is pushing a mass along this curve C, how much work is it doing? And remember, when we talk about work, work is force times displacement. So one oldie but goodie that we have to dig up, the dot product. Remember, a dot product between two vectors on one hand can sort of signal for us how close those vectors are to pointing in the same direction. If they're parallel, that is pointing in the same direction, I don't mean opposite, but exactly the same direction, the dot product will be positive. If they are perpendicular or orthogonal, the dot product will be 0. And then if the angle is bigger than 90 degrees, if they're pointing in opposite directions, the dot product will be negative. And that will be relevant here. We didn't talk about this too much, but the dot product also can help us find work. That is, if F is a force and, well, here we'll use V as a displacement vector. So you can imagine pulling a rope that's attached to, say, a sled on the ground. You're not pulling the rope directly in the direction of motion, but you're still doing work by pulling that rope and moving the sled. So F dot V will give us the work done. It accounts for the angle. So here's our plan. Here's how we will come up with this path integral, or sort of a Riemann sum definition. Imagine this black curve is a curve C that lives in a vector field. So I didn't draw the vector field, but C cuts through it. The idea will be kind of like it's been with other integrals. We'll chop it up. So we could think of C as being our sort of region of integration, or our interval over which we're integrating. We'll chop it up into sub-intervals, that is, into smaller paths. And we can imagine each of these as being a displacement vector. So when I chop it up this way, C looks sort of piecewise linear. Well, it doesn't have to be, but as these subintervals get smaller, they'll better approximate the curve. And now a vector field, remember, it's defined at every point, and the vectors could look a little different as we move from point to point. But the idea will be that as these subintervals get small enough, the vectors won't change very much on each of them. So now, along each piece of this chopped up curve, we can evaluate the vector field, that is, look at the vector F evaluated there, and we can estimate whether the vector field is helping or hindering us as we move along C, or how much work it's doing, by taking a dot product. That is, we'll take a dot product of this linear approximation piece of C and the corresponding vector in the vector field. And we can do that for each of these pieces, how much work is done to get us from R0 to R1, from R1 to R2, R2 to R3, and so on. And then the last step, just like for our other forms of integrals is to add all these up. Well, actually, we'll add them up and take a limit. We'll let these subdivisions get smaller and smaller and smaller. We'll add all of them up, and that's the thing that we'll call our integral, our path integral, or our line integral. So this is the notation we'll use, and we call this the line or the path integral of the vector field f over the curve C. So let's look at some examples. Actually, first, let's talk about notation. If you have seen this in a physics or an engineering class, you may have seen it written differently. That is, if we can write our vector field with components P and Q, you might see a line or path integral written this way, sort of distinguishing the two components of the vector. And then in a special case where our curve or path C is closed, and that just means it starts and ends at the same place, then we give our line integral a special name. We call it a circulation integral, and we denote it this way. Let's look at some examples. In each of these, we'll let C be a circle that's centered at the origin, and the path goes counterclockwise around it. And I want to estimate whether the circulation is positive, negative, or zero. That is, imagine that you're canoeing along this circle, going counterclockwise. I want to know, is the vector field helping you or hindering you? And sort of the net effect. So the answer might be helping at one point and hindering at another. We want to know what's the net effect. So if we look at this first one, when we're in the first quadrant, I think you'd agree the vector field is definitely helping. It's moving us up as we're going up and to the left. In the second quadrant, it's helping again. It's pushing us down as we're moving down to the left. And in general, anytime we're moving up, the vector field's pointing up. That is, in the right half plane. When we're moving down, the vector field's pushing us down in the left half plane. So the net effect here is the vector field is helping. So this is a positive circulation vector. I'm sorry, circulation integral. The next one, in the first quadrant, the vector field is helping, but in the second quadrant, as we move further counterclockwise, the vector field is sort of pushing us back in the opposite direction. We could think of it as canceling out the help from the first quadrant. And the same will happen in the bottom. It helps a bit, but then sort of opposes us as we come back around to the start. So since these cancel out, this is a circulation integral of 0. Or put another way, if this was a force field pushing a mass around this circle, the amount of work the force field does is 0 at the end of the day. This radial vector field, well, at any point on the circle, these vectors are always perpendicular to our direction of motion. So that is, they're not moving us forward or backward. They're always sort of almost irrelevant to our direction of motion. So there's no work being done by the vector field. It's not helping us. It's not hindering us as we move around the circle. So that's a circulation of 0. And the last one, well, I think this one is pretty easy. At every point, as we move counterclockwise, the vector field is always pushing us exactly backwards. It's always opposing us. So this would be a negative circulation. So we'll see some more examples of these in class, and in the next video, I'll show you how to compute a line integral